Hi, welcome to the Calculus 3 lecture series. And we are in the unit talk about the vector calculus. And this is our video number 7. And we're going to talk about the curl and the divergences here. Okay, so this section in the, in this lecture, we're going to cover the described two operations in the 3-dimension space, and it's very similar like the differentiations here. So the names we call it curl and the divergences is from when we modeling the fluid flows here. Okay, so let's go ahead and get a start. And okay, so also like in here, let's go ahead and take a look at our lecture notes here. And also in here, I'm going to, after we did a basic introduction, I'm going to put out a couple of videos from the Khan Academy. And so you'll be able to see kind of the visualization about what is a curl and divergence means here, okay? So we know the curl and the divergence both is the operations here, okay? So when we say the curl, let's take a look at what is the curl means, and then later we'll watch the video, so maybe you will get a better idea here. So the curl at a point, okay, at a point in the vector space, okay, in the curl at a point, well, let me say that maybe it's better is here. You know, when you get a curl at a point, okay, so the curl is a vector, okay, and this vector measures the rotation. So the rotation of the fluid about a point in the flow. Okay, so and then what is the divergence here? Divergence here, div is here. So we say the divergence here at a point, okay, is a number. Okay, let's measure the rate of the change. The rate of the change of the fluid flowing from the point, okay? So basically we say it's kind of like the how fast is the fluid diverging from the point. Okay, so from these definitions here, so let's take a look at a few key things here. The curl is a vector, and the divergence here is a number, it's a scalar numbers here. So that's why if for given vector fields, right? So given vector fields here, so if for given vector field, okay, F here. So we said F is the vector field. Now, first things from the list definitions, we know the curl of F. What is here? This will be a vector, come out with vectors. So the first thing is be careful. Then the diversion of the vector fields here for given vector field. So what is here is a scalar, right? So it's a numbers here, okay? And so also the operation we described, we also introduced an operation we called this is this is the operation, the like upside down triangles, right? So this operation we call this the del operator. Okay, so and this operation is like what we have here is like a rho x I and plus rho y what j and plus rho z to the k here. Okay, so it's kind of like it's del is kind of like the partial derivatives for the components. We kind of deal with this at the beginning few sections, these units here. So we know like a del f here, right? So if f is a real value functions, then the del f is vectors here. What do they give you? They give you f of x, f of y. That means you take a partial for x and then take it a partial for y here. Okay, so the way we defined, so we know the curl is what? Is a vector. So the way we defined the curl, okay, so is what? Is the, so we'll say the curl is defined is will be you use these operations and the cross product vector field, right? So of course here the F here is the vector field in the 3 dimensions. So you will have a P like X, Y, Z, I plus Q, X, Y, Z, J, and R, X, Y, Z, what? Y, Z case here. So the way we define the curl is what? It's a cross product, right? So this is very important, it's a cross product. And then we define the divergence, the div for the vector field. So we say it's number. So the way we defined it is like this operation dot product, the vector fields here. Okay, so we know the dot product ended up is a real number. So that's why the divergence field is a scalar here. Okay, so that's why the curl, the way you can see here, right? So the curl is because you use this operation, cross product the vector field, right? And so then so if the here, so you should see, you should think the curl is some type of the what? So it's some types of the derivatives, right? So some type of the derivative for the vector field. Okay, so it's kind of like because you're taking because the del's operation is rho k, rho x, rho y, rho j, right? So it's some kind of derivative for the vector field, the capital F of x, y, z here. All right. So if F is the velocity of the fluid flow, then the curl F is measured the circulation per unit area, right? So for examples here, if we say the vector F here is what? Is a fluid flow. Okay. So if the is the velocity of the fluid flow, now we know the curl F here measures how, what is the measures here? It measures the circulation. So it's measure the circulation per unit square. Orthogonal to this vector field, f of x, y, z at this specific point, right? So at this big point, x, y, z here. If curl equal to 0, that means there's no circulations, right? And through, there's no circulation about the point and through the flow or through the point with the velocities here. And the direction of the curl is the axis of the rotations around the points here. So you use, we call it the right-hand rule to determine the direction of the rotations here. So so then the number of if you take the length of this, see the magnitude of the curls here, right? Because we know the curl F is a vector, right? So you take the magnitude of here. So what is this ones here? This ones here, they measures, right, the speed of the circulation. Of the circulation. About the axis, all right? Okay, so that's basically, yes. So the curl, okay, so you cannot with a vector, the divergence is the numbers here. So this is a basic what we covers here. So now if you go ahead, take a look, see here. So let me see here. So that means okay, so go to here. Okay, so here, okay, so this is a summaries here about what we just did here, right? So the curls here is a point, is a vector, and is measure the rotation of the fluid about the point. Then divergence here is a number, is measure the rate of the change of the fluid flowing from the point to point. And then we defined this del operators, right? And so then we defined, we say, okay, the curls here is here's our definition, is the cross product, right? So it's an operation. So we learned in the earlier, like when we talk about the geometry space, we talk about the cross product. So that's how do you calculate the cross product, right? So then the cross product here and will be the del cross F. So if you put the components in there and what you get here, so you will get here is the formulas here. So I'm pretty sure, everybody can do the mechanical part very well. And so now that's in here. Let me try to, put out let me try to pull out the video so you can get like the intuitive idea of what is a curl and the divergence. Then we are going to work on the mechanical part, right? So we're going to take a look at the formula, how that the formula works here, all right? So let's go to take a look at this video first. And I hope after this video here, you will be able to get a pretty good understanding about the curls here. Okay, so let's go ahead, take a look.
Remember, we don't always draw every single vector. We just draw a small subsample. But in principle, every single point in space has a vector attached to it. You can think of each particle, each one of these water molecules or air molecules, as moving over time in such a way that the velocity vector of its movement at any given point in time is the vector that it's attached to. So as it moves to a different location in space and that velocity vector changes, it might be turning or it might be accelerating, and that velocity might change, and you end up getting kind of a trajectory for your point. And since every single point is moving in this way, you can start thinking about a flow, kind of a global view of the vector field. And for this particular example, this particular vector field that I have pictured, I'm going to go ahead and put a blue dot at various points in space. And each one of these you can think of as representing a water molecule or something. And I'm just going to let it play. And at any given moment, if you look at the movement of one of these blue dots, it's moving along the vector that it's attached to at that point. Or if that vector is not pictured, you know the vector that would be attached to it at that point. And as we get kind of a feel for what's going on in this entire flow, I want you to notice a couple particular regions. First, let's take a look at this region over here on the right, kind of around here. and just kind of concentrate on what's going on there. And I'll go ahead and start playing the animation over here. And what's most notable about this region is that there's counterclockwise rotation. And this corresponds to an idea that the vector field has a curl here. And I'll go very specifically into what curl means. But just right now, you should have the idea that in a region where there's counterclockwise rotation, we want to say the curl is positive. Whereas if you look at a region that also has rotation, but clockwise, going the other way, we think of that as being negative curl. Here, I'll start it over here. And in contrast, if you look at a place where there's no rotation, where like at the center here, you have some points coming in from the top right and from the bottom left, and then going out from the other corners, but there's no net rotation. If you were to just put if you were to put like a twig somewhere in this water, it wouldn't really be rotating. These are regions where you think of them as having zero curl. So with that as a general idea, clockwise rotation regions correspond to positive curl, counterclockwise rotation regions correspond to negative curl, and then no rotation corresponds to zero curl. In the next video, I'm going to start going through what this means in terms of the underlying function defining the vector field and how we can start looking at the partial differential information of that function to quantify this intuition of fluid rotation.
Okay, so I think this is a very good video, so you can get an idea about what is the curl mean. That means they are turning, and also in here you see a notice here. So in fact, when you turn the counterclockwise, so he has these two positive and the negative, the messed up here. Okay, so that is in the two-dimension curl. So what that means, you can see here. Okay, so the next things here I want to share is the one, how about if this is the three-dimensional curl, say then what's that mean? Here I just get the videos, the part is the kind of the most important part to demonstrate the idea. If you have time, you can go over, look at the whole video. I thought it's very, very good videos, all right? Okay, so let's
three-dimensional vector fields, like let's say this one that I have here. So I don't know about you, but for me, it's really hard to think about the fluid flow associated with this. I have a vague notion in my mind that, okay, like fluid is flowing out from this corner and kind of flowing in here, but it's very hard to think about it all at once. And certainly if you start talking about rotation, it's hard to look at a given point and say, oh yeah, there's going to be a general fluid rotation in some certain way, and I can give you the vector for that. But as a more loose and vague idea, I can say, okay, given that there's some kind of crazy air current fluid flow happening around here, I can maybe understand that at a specific point, you're going to have some kind of rotation. And here I'll picture it as if there's like a ball or a globe sitting there in space. And maybe you imagine your new vector field and saying, what kind of rotation is it going to induce in that ball that's just floating there in space? So maybe you're imagining this as like a tennis ball that you're sort of holding in place in space using magnets or magic or something like that. And you're letting the wind sort of freely rotate it, and you're wondering what direction it tends to rotate. And then when it does, and once you have this rotation, you can describe that 3D rotation with some kind of vector. And in this case, it would be a vector that points out in that direction, because we're kind of curling our right-hand fingers over in that direction. And if you don't understand how we describe 3D rotation with a vector, I have a video on that. Maybe go back and check out that video. But the idea here is that when you have some sort of crazy fluid flow that's induced by some sort of vector field, and you do this at every point and say, hey, what's the rotation at every single point? That's going to give you the curl. That is what the curl of a three-dimensional vector field is trying to represent. And if this feels confusing, if this feels like something that's hard to wrap your mind around, don't worry, we've all been there. 3D curl is one of the most complicated things in multivariate.
Okay, so this is how they derive, how they describe the 3D curls means and how is that rotation going on. So, okay, so now the next video I'm going to share is the video talk about the divergences here, right? So I think this video is pretty good to show you the concept about what does the divergence mean. And okay, so I think here, take a look.
Molecules or dots to represent a small sample of the water molecules throughout space here. And then I'm just going to let it play where each one moves along the vector that it's closest to. And I'll just let it play forward here, where each one is flowing along the vector that's touching the point where it is in that moment. So for example, if we were to go back and maybe focus our attention on just one vector like this guy, one particle, excuse me, he's attached to this vector. So he'll be moving in that direction, but just for an instant, because after he moves a little, he'll be attached to a different vector. So if you kind of let it play and follow that particular dot, after a little bit, you'll find him, elsewhere. I think this is the one, right? And now he's going to be moving along this vector, or whatever one is really attached to him. And thinking about all of the particles all at once doing this gives a good sort of global view of the vector field. And if you're studying math, you might start to ask some natural questions about the nature of that fluid flow. Like, for example, you might wonder if you were to just look in a certain region and count the number of water molecules that are inside that region, does that count of yours change as you play this animation, as you let this flow over time? And in this particular example, you can look and it doesn't look like the count changes, certainly not by much. It's not increasing over time or decreasing over time. And in a little bit, if I gave you the function that determines this vector field, you will be able to tell me why it's the case that the number of molecules in that region doesn't tend to change. But if you were to look at another example, like a guy that looks like this, and if I were to say, I want you to focus on what happens around the origin, in that little region around the origin, you can probably predict how, once I start playing it, once I put some water molecules in there and let them flow along the vectors that they flow along, the density inside that region around the origin decreases. So we put a whole bunch of vectors there, and I'll just play it for a quick instant, just kind of let it jump for an instant. And one thing that characterizes this field around the origin is that decrease in density. And what you might say, if you want it to be suggestive of the operation that I'm leading to here, is that the water molecules tend to diverge away from the origin. So the kind of divergence of the vector field near that origin is positive. And you'll see what I mean mathematically by that in the next couple of videos. But if we were to flip all of these vectors, right, and we were to flip them around, now, if I were to ask about the density in that same region around the origin, you can probably see how it's going to increase. And when I play that fluid flow over just a short spurt of time, the density in that region increases. So these don't diverge away, they converge towards the origin. And that fact actually has some mathematical significance for the function representing this vector field around that point. And even if the vector field doesn't represent fluid flow, if it represents like a magnetic field or an electric field or things like that, there's a certain meaning to this idea of diverging away from a point or converging to a point. And another way that people sometimes think about this, if you look at that same kind of outward flowing vector field, is rather than thinking of a decrease in density, imagining that the fluid would have to constantly be repopulated around that point. So you're really thinking of the origin as a source of fluid. And if I had animated this better, a whole bunch of other points should be sources of fluid so that the density doesn't decrease everywhere. But the idea is that points of positive divergence, where things are diverging away, would have to have a source of that fluid in order to kind of keep things sustaining. And conversely, if you were to look at that kind of inward flow, or what you might call negative divergence example, and you were to play it, but it were to go continuously, you'd have to think of that center point as a sink, where all the fluid kind of just sort of flows away. And then that's actually a technical term. People will say the vector field has a sink at such and such point, or the electromagnetic field has a sink at such and such point. And that often has a certain significance. And if
Okay, so I guess from this three video, and you'll be able to see, what is the visual presentation of the curl and the divergences here. Okay, so that's what we defined the curl. So this is a mathematical term. So I think for our first video, we'll stop here. And then for our second video, we'll start going to do some problems about the, how to do the calculations and what are the good theory and the characteristics we have here. All right. Okay, that's it. So let's stop here.